Hello, and welcome to this presentation on the topic of monitoring blood alcohol content using a device made from commercial off-the-shelf sensors. My name is Tristan Novak, and I'm from NC State University. Blood alcohol content, or BAC, above a certain threshold can impair a person's reasoning ability and motor control. These two factors, combined with a slow reaction time, can result in dangerous situations while driving a vehicle and/or making decisions. Therefore, it may be useful to have a personal device for monitoring BAC when consuming alcohol. One such device is the breathalyzer, which measures a person's BAC from their breath sample. The ultimate breathalyzer would be small, cheap, accurate, easy to use, and easily sanitized so others could use it too. My colleagues and I have created a Bluetooth-enabled breathalyzer that attempts to handle some of these challenges. To create our device, we used an Arduino Nano, which interfaces with an alcohol sensor, a humidity sensor, and an Android tablet over Bluetooth. We also brought 3 commercial off-the-shelf breathalyzers into the study for comparison. So here's a diagram of our system. In the top right, we have a 9-volt battery powering the system. There's an analog alcohol sensor, which is biased with a 10K resistor, and a resistive heating element. There's also an analog humidity sensor, which was used to verify an accurate breath sample. The Arduino communicates to a Bluetooth transceiver over its UART. Here's a picture of the finished product. We incorporated sanitation by using disposable mouthpieces. On the right is the inside of the enclosure with space for the battery. Now I will tell you a little bit about how the Android and the Arduino communicate with one another. First, the user powers on both devices and opens the Android application, which consists of a Python script and HTML GUI. The user is prompted to select the correct Bluetooth device. The user presses the Start button on the application, which requests a test from the Arduino. If the Arduino replies with a ready signal, the app prompts the user to blow. After the Arduino receives enough data, it calculates the BAC and sends it back to the Android for display. If the Arduino does not receive valid data, it sends a failure code to the application, upon which the user is given the option to retry. The most interesting part of the project was the data analysis. We proposed 4 different ways to calibrate our new breathalyzer. One option is to compare the sensor readings to a BAC obtained by drawing and analyzing a blood sample at several different data points, but this method would be very invasive. We could also have calculated a BAC based on information in the alcohol sensor's datasheet. This would require creating a calibration solution of 0.4 milligrams alcohol per liter of clean air, and then compensate the readings for temperature and humidity, and then find some way to convert milligrams per liter into BAC. A third method was to calculate the person's BAC based on their body weight, metabolism, alcohol consumption, time lapse, and other data. Finally, the way we implemented our calibration was by calibrating it against the readings from the 3 commercial off-the-shelf devices. So, to do this, we had 4 participants who were administered incremental amounts of alcohol, with a 20-minute time lapse in between doses. This was to eliminate interference from mouth alcohol. After each dose, the sensor value was recorded using our device, and the BAC was read by the 3 commercial off-the-shelf systems. One breath analysis with our device was based on about a 1-minute sample of alcohol and humidity readings, each taken at a frequency of 1 Hz. Each reading was low-pass filtered by averaging 5 ADC conversions. This test was repeated until enough data points were captured. Here's an example exhalation profile of alcohol sensor readings and humidity readings. The samples are taken every second for 45 seconds. There are 2 key points to this graph. One is that there's a clear maximum of the alcohol sensor value, and the second is that there is a clear increase in humidity, which was used to verify the breath sample. So now the BAC readings from the commercial off-the-shelf devices were plotted with respect to the alcohol sensor readings, as shown in this graph. These data have an exponential trend. A minimum threshold was applied to the exponential data, thus generating a piecewise function, as shown here. This function was then implemented in the Arduino to calculate a BAC based on sensor value, which in this equation is the variable x. Now the new formula was applied to the calibration data, and the error was calculated with respect to the average BAC of the 3 commercial off-the-shelf devices. At a BAC of 0, all breathalyzers agreed. At very low BACs, less than 0.01%, there were a lot of inconsistencies between different breathalyzers. In BAC ranges from about 0.003% to 0.04%, the homemade breathalyzer agreed more closely with the off-the-shelf breathalyzers than it did at higher BACs. The average percent error was 24.17% for the Backtrack S35, 40.62% for the keychain, 33.3% for the Aura, and about 30% for the homemade breathalyzer. The breathalyzer our team created overcame a key shortcoming of the commercial devices, which was immediate feedback during testing. The 3 commercial devices relied on sound to alert the user when to blow and to stop blowing. But we could eliminate the noise by using the app, thus making the event less noticeable by others in a public space. We also used cheap disposable mouthpieces and kept the overall cost to a minimum. Unfortunately, the alcohol sensor we used had high power consumption and was relatively large in size. All the devices required a time delay to allow the sensor to air out, but our device took much longer than the commercial off-the-shelf devices. And here's just a few observations on the off-the-shelf devices. The Aura was the most expensive and had an extra significant figure, but was not necessarily more accurate. The Aura also required a really hard blow, which was sometimes difficult to provide. And finally, it was really interesting that the BAC readings by all the devices had a large variance. They did not agree that closely with one another. So here's a quick demonstration of the project. We have the Bluetooth breathalyzer powered on with a mouthpiece inserted, and we have the app running on a Nexus 7. So first we press the button to start and it prompts to blow, so I'll blow into this. And then once it shows up a BAC, then I can stop blowing. And so it looks like I have blown a 0.01. Here's the references. Thanks for listening, and if you have any questions, tweet them using the following hashtag.